Good morning. This is lecture number 5, Measurement Science, Monday, 25 November 2013, University of Twente, the Netherlands, taught by Edwin Carlin, currently at the University of Tsukuba in Japan. Please pay attention to Blackboard. Homework assignment number 5 is now posted on Blackboard, and you can download it and start working on those exercises. And homework number 3 is due today. In this lecture, which is quite long, we're going to cover 2 topics. The first one, signal conversion and sensor interfacing, and the second topic, signal processing. Now, under signal conversion and sensor interfacing, we're going to talk about amplifiers, bridges and nulling, modulation, demodulation, and synchronous detection. Now, the amplifiers and the bridges, these are primarily review, so we're going to go very quickly over these topics. But you can go at your own pace with the slides that are on Blackboard, and then the basic concept of nulling. And then likewise, for signal processing, the analog and digital filters I think that you've had some exposure to. These are primarily with optical filters, and there's a bit of digital filtering, the basic concepts. And then we will go quickly over those topics, and then we'll talk about A to D and D to A conversion with a little introduction about the format of digital numbers and the different binary coding that you can do with different A to D and D to A converters. Sensor outputs often take the form of voltage signals and therefore can be processed directly. Signals often come in other forms: translational displacements, resistance, inductance, capacitance, current, frequency, phase, etc. And therefore we need a variable conversion element to convert these into voltage signals that we can apply conventional signaling units to be able to interpret and to do calculations with our sensor outputs. We have our 5-block measurement system diagram, and we're going to be covering these variable conversion elements today and also signal processing. Analog amplifiers, operational amplifiers, non-inverting and inverting amplifiers, instrumentation amplifiers, and I to V current to voltage conversion, bridges and nulling are the topics we're going to cover first. An ideal operational amplifier is one where we have an amplification factor A0, which we assume to be infinitely large, an infinitely large input impedance, where we assume that the input currents at terminals, the negative and positive terminals, are 0. The common mode rejection ratio is infinite, which means that the input on terminal plus and terminal minus are rejected on the output. The common signals that we see on those are going to be rejected in the output because it's a differential input. The offset voltage, V out, when both of the terminals are set to 0, then we assume that the output voltage is 0, and that's not always the case. The bias currents at the input terminals are 0, and the output impedance is 0 and not dependent on our load. And in these cases, the ideal operational amplifier feedback is required. This is an example of a bipolar transistor operational amplifier. Most of the circuit elements that you see in this diagram are due just to set up the bias currents within the structure. You'll see in the blue dotted line, we have the differential input, where we have the positive terminal, the inverting terminal, and the non-inverting terminal. And then we also have a connection point to be able to null the offset, to make sure that the output voltage is 0 when the input signals are 0. We have current mirrors in this structure to help set up the bias currents, that help set up the operation, to make sure that the operational amplifier is operating in a linear region. And then because this does amplification, then we have output amplifiers in an output stage that basically allows you to source higher currents so that it doesn't affect the frequency response of the system. And the capacitor circled in red in the center is called the Miller capacitance, and this is basically a tuning capacitor to set the stability of the amplifier, because we have a lot of capacitors within this system, and we want to be able to set the frequency response and the phase response to the system so that it operates in a stable regime. This is an example of a bipolar operational amplifier with JFET inputs. On the previous slide we saw a bipolar junction transistor. Those are usually very fast. They consume a lot of current, but they also have a lot of input current associated with their input terminals, which is not always what we want. In this case, we compromise and we make a bipolar junction transistor operation unit, and at the input JFET, so we have very, very low input currents to this system. We have all the same type of biasing elements. You'll see in the lower left part of the circle we have our differential input with our JFET transistors. And then in the surrounding periphery you can see all of these current mirror structures that set up our bias currents. And on the output we basically have our amplifier and then our source follower to be able to source currents to drive particular high current loads. And this is an example of a CMOS operational amplifier. Again, it has the same sort of blocks, the input stage with the differential input, with our inverting and non-inverting terminals. The setting stage, as it's labeled here, basically the current mirrors to be able to set the current for our amplifier units. Our output stage that does both amplification and then provides output currents such that the system can source and drive larger loads. You'll also notice that there are capacitance networks to be able to set the stability, these Miller capacitive compensation to improve stability of the network and the operational amplifier. So the main operational amplifier stages are the differential amplifier, provides low noise amplification, high input impedance, and usually a differential output. The voltage amplifier provides high voltage gain, single pole frequency off, usually single-ended output. And the output amplifier provides high current driving capability, low output impedance, and current limiting and short circuit protection. And then we have the Miller capacitive compensation strategy to improve the stability of the operational amplifier. Well, based on the complexity of the number of elements in an operational amplifier, obviously it's not an ideal type of element. And this is an example of modeling the 9 idealities of the operational amplifier. We have voltage sources to represent the offset voltage, the input noise voltage, which is lowercase vn, the finite currents at the input terminals IB minus and IB plus, the finite input impedance Rin, the finite gain of the system, which is represented by a voltage source with a gain A, and then our output impedance, which is not 0 and it's finite. So the important properties of an operational amplifier, and I'm not going to go over these. These are expected to be prerequisite knowledge for the course, but input offset voltage VOFF, input bias current, offset current, temperature coefficient, DC gain, input impedance, common mode rejection ratio, supply voltage rejection ratio, unity gain bandwidth, and slew rate. Slew rate, if you haven't seen this, this is the ability of the operational amplifier to respond to the rate at which it can respond to voltages that are changing. This is an example of a data sheet for an operational amplifier. I won't go over this in detail. These are the types of things that you should have already experience with at this point in your careers. But when you pick an operational amplifier, the first thing you do is to go to the data sheets to look at the particular operating characteristic that's most important for your design. If it's a low input noise voltage, if it's the bandwidth, if it's the frequency response, the driving current, the output impedance, etc., you can check it in the data sheet. Non-inverting amplifier configuration, where we have the input voltage connected to the positive terminal and then a feedback network to the negative terminal. We can derive the transfer function for this system. A buffer amplifier, where the output terminal is connected to the negative terminal, and then we drive the operational amplifier at the positive terminal, and ideally we get a gain of the system of 1. A difference amplifier, where we have again the feedback network to the negative terminal, and we apply voltages V1 and V2 to the negative and positive terminals respectively, and then we terminate also with a network the positive terminal to ground, and then V out is a ratio of R2 over R1, and then the difference of V1 and V2. Now if we want to do current to voltage conversion, the naive way to do it is to just apply a current to a resistor and we get a voltage drop, and therefore if we have a voltage drop across then we have a voltage output. That's all fine. However, as soon as we connect a load resistance to the system, the output then is no longer proportional or no longer equal to the current times the original resistor R, because now the current will be split. So then the output voltage then becomes a value that's split. Also, we have a source voltage in the current source that's going to take away some of the current as well. So how do we do this current to voltage conversion in a clean way? One way is to use an operational amplifier. So we provide a current and we drive the amplifier into the negative terminal, which has a feedback resistor connected between the output terminal and the negative terminal of the operational amplifier. Now how does this work? Well, as we've talked about in previous lectures, when you have the positive terminal connected to ground and the negative terminal connected to a feedback network and into your input, this is a virtual ground. So the input terminal is essentially set at 0. So your output is always going to be minus R times the original current, because you have this virtual ground. So R has no influence on the output current. It's always going to be determined by the current that's going through IR. RB also has no effect on the input current. So you can see that throughout the course, this course of the lecture, or throughout the courses of the lectures of the course, we've seen this virtual terminal concept, which is one of the most important uses in measurements of the operational amplifier. Now, the operational amplifier also has finite gain, and we have to take that into consideration. This is an example of connecting a operational amplifier with a feedback network, and as long as A0 is quite large, then we can say the output is the transfer function of the system V out over V in is then 1 plus the ratio of R2 over R1, which is 1 over beta. However, since A0 is a function of frequency, then we basically have a pole that's introduced at the bandwidth of the operational amplifier. So A is equal to A0, this is the DC value of the gain of the system, divided by 1 plus j omega, and that's the time constant, or basically the bandwidth of the operational amplifier. So in reality, we have to modify our original representation of the operational amplifier when we include a frequency response with feedback. And we do this using this block diagram with beta now, that's the gain from our operational amplifier. And our new transfer function now is going to be V out over V in, which is equal to A0 divided by 1 plus j omega tau sub V plus A0 times the gain due to the feedback network, which then is A0 divided by 1 plus A0 beta divided by 1 plus 1 divided by 1 plus j omega tau V over 1 plus A0 beta. Now, the gain bandwidth product is an important concept here, and you can also see that the gain of our system is defined as A0 divided by 1 plus A0 beta, and the unity gain bandwidth is when the bandwidth is when the gain is equal to 1. So remember these basic transfer function for this finite gain of the system and also the frequency dependent gain of the system. Now, an important amplifier in measurement systems to be able to get high input impedance and also high gain is to use a two-stage amplifier. This contains 3 operational amplifiers, 1 amplifier per input voltage, and then an output amplifier to provide the gain, and this is the transfer function representation for that. So an instrumentation amplifier has 2 inputs and 1 output. Now, it's very important because we can provide signals to the operational amplifier to both inputs. And we can provide an output voltage that is proportional to the difference between two inputs. These types of amplifiers offer low offset voltage and very high common mode rejection ratio. And interestingly enough, the gain can be basically set by a single resistor for these systems. They're very powerful, so you should be a little bit aware for doing sensitive and robust measurements. Sometimes an instrumentation amplifier. It's a little more expensive, but it can provide much better performance than a single operational amplifier. So that concludes our operational amplifier overview. That is a review for you, so hopefully none of the concepts that were covered in the last 20 minutes are new to you. If they are, then you better brush up on your basic circuit theory for operational amplifiers because it's expected to be known. Now we will move on to signal processing, bridges, and the concept of nulling. Bridge circuits are often used to produce an output in the form of a voltage that changes as the measured physical quantity changes. They provide an accurate measurement of resistance, inductance, and capacitance. An example that you've already seen is the piezoresistive strain sensor that produces resistance changes due to strain-induced bending, and we use a bridge to be able to read this out. The null-balanced method of output indication is widely used in instrumentation and sensor applications. And nulling means that we try to set the output of our system to 0. We null it. Okay. A commonly used example of null balance is the bridge circuit. And this is a bridge that has two arms. The first arm contains resistors R1 and R2. The second arm, R3 and R4. And then the output voltage is simply the difference between the voltage division between the first arm and the second arm. Now, in equilibrium, all resistances have equal value. R2, R3 is equal to R1, R4. That's in equilibrium. Now, there's an entire theory around doing null-balanced circuits. And if we consider a null-balanced circuit as a passive two-port connected between the impedances Z0 and ZG in this diagram, which these could be a load is Z0 and ZG is a source resistance, and we have a null-balanced circuit that's connected between these. If we assume a balance condition, therefore the 0 output voltage, and we do the computations of these different coefficients, the main result from using these null-balanced circuits, the balance condition is independent of ZG and Zout, which is fantastic, right? Because we always have these problems associated with the load that we have to drive and the sensor configuration that provides a finite resistance or a finite current or a finite voltage drop across the sensor that always introduces some bias to our measurement. So using these null-balanced circuits, we can get rid of some of these biases. Now, the bridge configurations that we're concerned in this class are primarily the single element, which is V out, approximately equal to 1 over 4 delta R over R, VI. Now I say it's approximate, this is a nonlinear representation. Half bridge, it's 1/2 delta R over R times input, and a full bridge, V out is equal to delta R over R, VI. So the advantages of using single element bridge mainly is that you only have one element that's changing in the bridge. So it's easier to realize this. It's less expensive, at the expense of the fact that it's not completely a linear response, and the sensitivity is smaller than the sensitivity of a half bridge. So then a half bridge is that you have two of the elements that are changing and two that are not changing. So in this case you get higher sensitivity. It's a little bit more linear, but then the disadvantage is that it's a bit more complex because you have two that are changing in a similar way. And then a full bridge is that all four elements are changing. We saw in some of the previous lectures. Provides the highest sensitivity, the highest linearity, but also the disadvantage is it requires the highest level of complexity. So it's more expensive and it's more difficult to find sensors that really change in exactly the same way so that you can take advantage of all four elements changing. It's not impossible, but it's just a bit more expensive and time-consuming, higher complexity. You can see more information on disbalanced and null-balanced bridges in Chapter 5 of the book. over a few examples of bridges. This is a null-type DC bridge where we have the input VI is connected to terminals A and C, and in the output we read between D, B, and essentially the component RU that you want to read out is then a ratio of R3 times RV divided by R2, and RV can be variable. So you can determine what the resistance of an element is by varying RV and then having R2 and R3 set. Type AC impedance bridge, if you have an impedance that you want to read out, ZU, you use the same basic concepts. You have fixed resistances R1 and R2, and then you have an impedance ZV that you vary, and then you can find the output impedance that's a function of a ratio of R1 over R2 times the variable impedance. Now, if it's capacitive, then ZU is equal to 1 over j omega Cu. Then obviously the impedance ZV should be a variable capacitor. If ZU is inductive, then you also have to use a variable inductance as well for your readout. A null-type AC impedance bridge, and this is sometimes called the Maxwell bridge. You can go over these basic derivations on your own to make sure that they make sense. The applications of this are to be able to determine impedance values of an inductor and a resistor, for example, using a capacitor and a resistor. So capacitors are more easily accessible in resistors, and then you have a variable resistor here, so you can read out an inductance using a capacitive type of bridge structure, which is quite useful. Now, this type of bridge, the Maxwell bridge, can be used to measure the Q value of a coil directly, which is quite valuable, quite interesting. Okay, so we move on now to resistance measurements. We'll look at three basic types: DC bridge, a voltmeter, ammeter method, and then the ohmmeter. So voltmeter, ammeter method. Two methods, A and B. Measures the current flowing in both the voltmeter and the resistance, and the error is minimized when RU is much, much less than the resistance of the voltmeter. And in part B, measures the voltage drop across the unknown resistor and the ammeter, and error is minimized when RU is much, much greater than the ammeter. This is quite obvious, right? Resistor ohmmeter, in this configuration, you can see that we apply a potential. We have variable resistor RV and R1, and we connect a resistor RU that we want to determine across the output, and then we get RU is equal to R1 times the difference of VB and VM over VM. And VM is the voltage applied across the bias. VM is what you measure across your RU, and VB is the voltage that's applied with the source inside the dotted rectangle. Inductance measurements, we can use an AC bridge for accurate measurements. It's a simple method where we essentially have an AC source with a variable resistor connected directly to the inductance. and we measure the voltage across both of the inductor and the resistor, and then we can compute the inductance of the system, which is basically the square root of the square of the resistor minus the resistance of the inductor divided by 2 pi, the frequency of the system. We can also use the AC bridge for accurate measurements. Very simple. We can use the same concept and then include a capacitor in series with the resistor. So those basic methods round out resistance measurements. They're quite simple. Read through this on your own, and if anything doesn't make sense or if anything isn't clear, please contact me directly via email. Next, we move on to modulation, demodulation, and synchronous demodulation. So modulation and frequency conversion, modulation and mixing, frequency spectrum of AM signals, and then modulation methods and examples. There are many ways to embed a message in a carrier. We can use amplitude modulation, phase modulation, frequency modulation. In amplitude modulation, we want to multiply a signal by a sinusoid carrier, and this is called amplitude modulation. And AM shifts the frequency components of X by plus or minus omega C. So we have our input signal, and we multiply sine omega C, and then our output is going to be a combination of the multiplication of x of t times cosine omega C. And then you can see the frequency. We see the Fourier representation, where we have the cosine signal now, or y is equal to basically frequency components at omega c and negative omega c. And if our signal is located on the first dot, which is this dual lobe type of signature, then now the modulated signal will have that exact signal at this higher frequency. And you see that we don't have the signal at frequency 0 at DC. Now, you remember our discussion of doing measurements, DC types of measurements, low frequency measurements at higher frequencies to get rid of the 1 over F noise problem. And this is an exact type of method that allows us to take our low frequency signal, modulate it to higher frequencies, and then do our computation, and then we don't suffer from this 1 over F noise when we do our final determination of the sensor signal. Multiplying a signal by a sinusoidal carrier signal is called amplitude modulation, and this signal modulates the amplitude of the carrier, as I said. And this is another representation of that. So the carrier now, VC, is going to have this envelope that represents our input signal. The AMC signal frequency spectrum. So if we look at then, if we transform this into the Fourier domain, then what do we have? We have our signal at FC, and then you can also see that we have lobes. And these lobes are going to be due to FC plus the input frequency and FC minus the input frequency, these side bands. So the spectrum of the AM signal, we have these low frequency signals from the input signal, as we saw earlier, these side bands. And then we can also have another form of an AM signal where we have the suppressed carrier. So this is an AM signal with a suppressed carrier. It only transfers your input signal at the frequency Fi that's been modulated to this higher frequency Fc, which is our carrier frequency. So if we do this type of thing, then we need to have a modulator that can multiply our input signal and our carrier signal into one output signal. Now, in this case, we want our modulated signal to be double sideband suppressed carrier. So we don't want any carrier in the low frequency band, right? This is called double sideband suppressed carrier. So an AM signal with carrier is located on the top, and then an AM signal without the carrier is located on the bottom. One example of a modulator is a switching modulator, which basically makes this pulse, and we'll say that the amplitude of the pulse varies between 0 and 1, and V out is then the multiplication of the switch operation, the frequency of the switch operation in Vi of t, where S of t then can be expanded into this series representation. So the output ultimately is going to be V out is equal to Vi of t times S of t, terms of sums and differences, so the low frequency and higher harmonics are filtered. We can also do a bridge modulator where we have a bridge configuration with resistors R1, R2, R3 in this case is going to be a single element bridge, and then R4. Now, in this case, VR is our carrier signal, and our measurand, which is going to change in time, is the change in resistor, so delta R of t. At VA, we're going to have half the carrier. If we assume R1 is equal to R2, which is equal to VI of t over 2. At VB, we're going to have half the carrier with amplitude modulation. So VB is equal to VI of t divided by 2 plus delta R of t over R. And at V out, when we subtract these two, we're going to have our AM signal with no carrier. So if we modulate these signals, then at some point we do our detection, and then we want to demodulate them. And we do synchronous detection with this. So the demodulation, synchronous detection, and then we'll get into this lock-in amplifier. For AM demodulation, we can apply 3 different types of techniques. Envelope detector, which is very inexpensive. It's interference sensitive and phase insensitive. We can use a rectifier and low-pass filter, which is primarily a diode and a low-pass filter, which is reliable and phase insensitive. Or we can do synchronous detection, and this is multiply with a carrier signal and low-pass filter. Look at the synchronous detection. This provides us with the best ability to detect signals. X can be recovered by multiplying the carrier and then by low-pass filtering to remove the high-order components. So if we have y of t is equal to x of t multiplied by our carrier cosine omega c t, then z of t is going to equal y of t times cosine omega t We're going to multiply again by our modulation signal. And what do we get out of this? When we do that, we get x of t divided by 2 plus x of t divided by 2 type cosine 2 omega ct. So we're going to have our original signal at the DC position and frequency. And we're also going to have a signal located at the carrier frequency. And then we low pass filter to remove that high order component. So what do we have? Synchronous detection. We do convolution of frequency. So you see at our input, the magnitude of our input responses, we have our signal that's been modulated to omega c, then the Fourier representation of our signal. And then what do we get when we do the convolution in frequency? Then our z, our output of z, will have our original signal located at DC, but we also have components of our signal located at 2 omega c. We can recover x by doing low-pass filtering. So this just shows the basic equations for doing the synchronous detection. And then at the end, there remains this low-frequency signal. Basically gives you, with some multiplying coefficients, our original signal cosine omega I of t. And then we also have a phase term that we have to deal with. So the noise reduction using synchronous demodulation is shown in the 3 plots on slide number 58. So in the top plot is our original measurement signal, and all of these plots are in the frequency domain. So we see our original measurement signal is the blue spectrum located at our original location. It could be DC frequency or a low frequency. And then the middle plot shows the spectrum after modulation and amplification. So our original measurement signal now is amplified, and it's pushed back or pushed to the higher frequency FC, which is our carrier frequency from the modulation. And then due to the amplification, we have some noise at this original measurement location, offset, drift, 1/f noise, as we talked about earlier. And then the next step in the process is to demodulate the signal. And the lower plot shows the spectrum after demodulation. So then our original measurement signal that's been amplified is folded back to the original measurement location. The noise signals and spectrum, due to offset drift and 1/f noise, are now pushed out to the carrier frequency of the demodulation process. And also we get an image of our measurement signal at 2 times the carrier frequency when we do the demodulation. And then the final step in the synchronous demodulation process is to perform low-pass filtering, which will remove the noise contributions at the carrier frequency, and then also the mirror image of the signal at the 2 times the carrier frequency. You'll notice that we will always have this broadband white noise, which is located in the purple region. So we can't get rid of this random noise. We can reduce its effect by averaging, but we can never completely get rid of it. Now, an example of doing this is something that I've done many, many years ago, is to design a capacitive sensor that changes when molecules bind on one surface. So on this top plot, you will see a capacitor. So the upper capacitive plate is located in gray. And then we have a lower capacitive plate, which is the separation distance is G. And these are all made in like the nano lab. I made these myself, and these are basically made from doped polysilicon and doped silicon, so these are highly conductive plates. And we put this into a solution and we let molecules bind onto one surface of this lower silicon plate, which induces a stress which basically causes the plate to bend. And when the plate bends, it changes the capacitance reading. Okay? So we get basically a capacitance change that's based on molecules binding on the surface. This is a capacitive-based measurement. So this is the circuit located in part A of the diagram, and we have a differential type of sensor. So the sensor that changes is CS, and then a reference temperature capacitor that does not change. We multiply one of the capacitor signals by -1, and then we send this into a charge integrating amplifier. You see CR, and then it has a feedback loop, which is CF-RF. We amplify, and then we do synchronous. So remember that this is a synchronous modulation. So the modulation comes from the source located at the beginning of the circuit. After we multiply, so now we have the change of the capacitance that's been modulated at this higher frequency. We amplify, and then we want to demodulate by doing a multiplication again with the carrier frequency, and then we want to do low-pass filtering. And this is the circuit on the green circuit board on the right that allows us to do that computation. And so what this allows us to do, you'll see on the right-hand side, you'll see a plot, log-log plot, and you'll see a red trace. So the red trace at 0 frequency is the 1/f noise. So what we do is we modulate this at around 30 kilohertz, and we do all of our measurements at 30 kilohertz, where we're really at the noise floor of our measurement circuit. And then we can get rid of this 1/f noise associated with the sensors and all of the electronics involved in doing the measurement. Now, a special case of this synchronous demodulation is a lock-in amplifier. And these are used to detect and measure very, very small AC signals down to a few nanovolts. Their accurate measurements may be made even when the small signal is obscured by noise sources many thousands of times larger. Lock-in amplifier used a technique known as sensitive detection to single out the component of the signal at a specific reference frequency and phase. So noise signals at frequencies other than the reference frequencies are rejected and do not affect the measurement. So this is what this is saying essentially, is that we modulate to a higher carrier frequency, and then we make a very, very precise filter to filter out only the signal in that modulated frequency range within a bandwidth that's less than 1 hertz. And that way, we can get around large noise amplitudes. So how does it work? The lock-in measurements require a frequency reference. Typically an experiment is excited at a particular frequency. The lock-in detects the response from the experiment at a particular reference frequency. So we have a reference frequency, we have a signal. So the voltage of the phase-sensitive detection from the lock-in amplifier is our signal, Vs, plus our signal from the lock-in, sine omega RT plus theta s from our signal, omega r is the reference, times theta times sine omega L from the lock-in plus theta of our reference. And then this can be expanded into two terms. Now, the PSD output, the phase-sensitive detection, it's two AC signals, one at the difference frequency and the other at the sum frequency. If the PSD is passed through a low-pass filter, the AC signals are removed. What will be left? In the general case, nothing. However, if omega r and omega L are equal, the difference frequency component will be a DC signal. And this is exactly what we showed in the synchronous demodulation. So we need to make the lock-in reference the same as the signal frequency. The frequencies and phases have to be the same, otherwise cosine theta s minus theta ref will change, and the PSD voltage will not contain the DC signal. In other words, the lock-in reference needs to be phase locked to the signal reference. And the lock-in amplifiers use a phase lock loop to generate that reference signal. And the PLL in the lock-in amplifier locks to the internal reference oscillator to this external reference, resulting in a reference sine wave at omega r. PLL actively tracks the reference. Changes to the external frequency do not affect the measurement. And you can go through these calculations and you can see that using this type of an arrangement, using this concept of synchronous demodulation, and also this lock-in technique allows us to measure signals that are far, far smaller than the noise signal, which were described early in the course as being very, very difficult to do. This is a diagram showing the basic configuration of a digital lock-in amplifier. This is a lock-in amplifier that I have in my laboratory that's used, and we have a low noise differential amplifier at the input, which is on the top left-hand corner. We have notch filters to get rid of line disturbances, a gain, and then you'll see that we have this quadrature operation where we have a 90-degree phase shift that's put into the reference signal that allows us to do this quadrature detection and then low-pass filtering, and then be able to provide the output at X and the output at Y. So if we look at some of the specifications for this system, full scale voltage, 100 nanovolts to 500 millivolts. The sensitivity in current, 100 femtoamps, up to a half a microamp. So the noise, 7 nanovolts per root hertz at 1 kilohertz, and 0.13 picoamps per root hertz. Typically, these systems don't work for very, very high frequencies because it's quite difficult to be able to lock on and do all of these operations at higher frequencies. But it's getting better. I think that there are some systems up to a megahertz or a few tens of megahertz, but they tend to be quite expensive. Okay, so now we're going to move on to signal processing and filters. So the analog filters should be somewhat of a review to you. These are basically analog filters that allow us to make low pass, high pass, and band pass filters. And digital filters we won't cover in this course. There's just too much material to cover. So most of the analog filters should be much of a review. It's more of an exercise in doing transfer functions to be able to look at the response of the system. So we'll talk about passive filters, active filters, integrator, differentiator, and then standard filters that are used in analog signal processing, such as Butterworth, Chebyshev, and Bessel filters. Analog filters, basically low-pass filters, high-pass filter, bandpass filter, and band-stop filters. These are the transfer functions for these systems. Passive and active filters. So a passive filter consists of impedances connected in a ladder network. Active filters contain an operational amplifier so they can provide gain. As I said, types low pass, high pass, band pass, band reject, or notch. First order low pass, general characteristics. You can go over this on your own to look at all of the characteristics. You should be able to derive the magnitude and the phase Bode plots, and we will have a homework assignment on this. A practical first order LP filter that considers a load. So the source and load effect in this configuration is going to affect the position of the pass band and then also the position of the band roll-off. First order high pass filter, again, I want you to know how to derive the magnitude and phase responses and then plot those on a Bode plot. High pass filter, this is an example. If your measurement signal is at 2 kilohertz and your noise is at 50 hertz, you want to be able to filter this out. Bandpass filters, if you want to do a series connection of low pass and high pass filters, you can basically make a ladder network to filter them out, and then you have the two frequency responses here. Higher order filters, basically cascading, series connection of first order filters H1, H2, H3. This is an example of the cascaded filters in some of the response, first order asymptotic, first order real, third order, and then the associated transfer function for these. So the design of active filters using operational amplifiers. We need to know how to derive our transfer functions. So now instead of just resistors, we're going to have impedances. So we make our transfer functions using impedances, Z1 and Z2 for example. So if we want to make an integrator, then Z1 should be a resistor and Z2 should be a capacitor, and then the transfer function accordingly. Integrator in the time domain obviously is 1 over RC in the integral of VI dt. The integrator frequency characteristic, it's more of a low pass filter. I want you to be able to know how to derive the transfer function, magnitude, and phase plots for an active low-pass filter. And these are examples of what those are. You should be able to derive those on your own. And then the integrator again, with another resistor connected to it to be able to push the passband out and to be able to adjust the time constant so you can extend the passband in the frequency domain. Then we can do a differentiator. Now Z1 is a capacitor and Z2 is a resistor, and then the associated transfer function. Differentiator in the time domain, and then the transfer function, so the differentiator starts looking like a high-pass filter, and then the associated amplitude-phase response in the complex domain, and then in the time domain. Then we can do a differentiator where we have both a differentiator and an integrator, and we start looking more like a bandpass filter, an active bandpass filter. So the standard filter structures, the Butterworth, Chebyshev, and Bessel. So the Butterworth is good because in the pass band it's as flat as possible. Chebyshev, it's as steep as possible, so you can get sharper cutoff between pass band and stop band, but then the flat band, the pass band, is not as flat as the Butterworth. And the Bessel has the best step response. So a Butterworth filter has this general characteristic and transfer function. Should be able to derive that. Third order Butterworth filter and the transfer function. So frequency characteristics, ideal for a low pass filter would be the dotted line, and then the 3 dB point. So you can see number 3, which is the Bessel function, which is the Bessel. So you can see the Butterworth has the flattest pass band. The Chebyshev has the steepest response, and then the Bessel is located at number 3. This is an example of a commercial Bessel Butterworth filter. You can do three-digit cutoff frequency resolution, and I believe you can do 8-order filters, and you can filter between 1 Hertz up to 500 kilohertz. And yeah, you can do up to 8 orders. In the roll-off, you can get 48 dB per octave. Very, very sharp filters. So you don't actually have to build your own filter. You can buy commercial filters that are extremely, extremely precise. Okay, that summarizes our really fast review over analog filters. And now we'll go on to the last part of the lecture today, which is A to D and D to A conversion.